So now we learned how to drive autonomously. But this algorithm we just learned in theory and we saw the code of, this is just a basic algorithm which is trying to avoid obstacles. But we want we want to race autonomously. And if we want to race autonomously, that means for us, we have to follow race lines and we have to follow this race line fast. So in the following chapter, I will show you what does it mean to follow the race line and to be as fast as possible. So the idea of this chapter is first of all to define what is the fastest way to get around the track. We need to understand here what is an optimization or an optimization problem, and we need to understand what is precise and accurate path tracking. Because that we know what is the best X and Y positions around the track, it doesn't mean that our car can follow that. And finally, what we will do here is we will implement a so-called pure pursuit path controller. That path controller is tracking our position. And here, for example, on the right side, you can see an example of racetrack and see its optimal race line with different colors that explain the speed we are driving here on. So, first of all, what else is needed to define actually our race line or our racing strategy for a given track? So what do you guys think? Do you think it's just enough to define a spline? Do you just think it's enough to define a path like the X and Y positions around the racetrack? Do you think that this is enough to actually race fast? The answer is no, because we need not only the X and Y positions, we need also the velocity profile. If we want to do that a little bit more enhanced, we need also an acceleration profile because, for example, we don't know what our car is using. And for example, we don't need only the X and Y positions, we also need, for example, the curvatures because we don't know what our car is using in the end to track its positions. So when you look at the racetrack, for example, here in this image, you see that we need the X and Y positions that define our path. Then we need a velocity profile based on these X and Y positions. That means just because that we know the path doesn't know that we drive fast as possible. And the fast as possible driving on racetrack, which means like high speeds, that is giving you finally a good lap time. And we define that as a trajectory. The trajectory is a combination of both the path and the velocity profile. And to be the fastest path around the racetrack, this is for us a so-called global optimal path, a global optimal race line. So in the next slides, we will talk a lot about the term called race line. The race line, per its definition, is the fastest trajectory around the racetrack. That means if you follow that race line with the declared speed, you will be as fast as possible. And now is the question, how do we create this race line? How do we get from a given track, for example, here on the left side, where you can see is the Formula E track in Berlin, how do we get from this racetrack representation to a racing line that fits exactly to that track here on the right side? So number one is you need to get information about the racetrack. An image here on the left side is definitely not enough. You need the exact representation of the racetrack, which means the inner bounds, the outer bounds. For both of the bounds, you need the X and Y positions, you need the heading, you need everything that represents your racetrack from a geometric point of view. So more or less you define the space where the car can drive. That's number one. For our F1 vehicle, we provided a bunch of racetracks, a 1 to 10 scale racetracks that you can use for this raceline optimization, or you can use to race on. And now is the question, how do I actually get this raceline? There are many opportunities or many possible methods you can choose from. There's not one single particular algorithm that is used, but there are many opportunities or many possibilities you can choose from to derive this raceline. In this lecture, we are focusing on the problem of a so-called optimization method or optimization problem. We know, or we worked with different algorithms. I have the paper here displayed, the source, the so-called minimum curvature trajectory planning and control for autonomous race cars, that is using this geometric representation of the racetrack, the inner bounds, the outer bounds, the center line information, and is creating an optimization problem. In this algorithm, you can choose from different options. Number one is showed here in blue, the so-called shortest path. In here, we creating a geometric quadratic optimization problem. The shortest path is trying to minimize the distance you are traveling. You see that here very good in the image, that you see the blue line is going on the inner bounds of the track. And for example, here from turn 2 to turn 3, it's going straight over this area because it's trying to minimize its path. So the shortest path, for example, is a good option because it's the shortest way you need to travel. When we're talking about race cars, we want not the shortest travel because we want to travel as fast as possible. Therefore, the second solution is the so-called minimum curvature optimization. This is showed here in green. What we do here is we create an optimization problem that's trying to minimize the curvature of the car, which means you minimize the steering input and you optimize regarding an optimal curvature profile, which means not many changes between the curvature and a steady increase of the curvature and then a steady decrease of the curvature. So overall, we minimize the curvature profile. A minimized curvature means for us that we drive as fast as possible and we can increase the speed and we can accelerate and decelerate constantly. This is showed here in green and we get a very, very good lap time based on this optimization. The third solution you have here is the so-called minimum time trajectory planning. What we're doing here is we are trying to find the minimum lap time and we are optimizing regarding the vehicle behavior on this track, speed, position and vehicle dynamics behavior to be as fast as possible and then to reach a minimum lap time. You see here the solutions first of all differ in computation run times. The shortest path is the fastest, just runs like 10 seconds. Minimum curvature runs like 30 seconds and minimum time trajectory planning runs like 5 to 10 minutes. In addition, the modeling depth for the vehicle dynamics for all of these optimization algorithms is increasing, which means you need more parameters, you need more accurate parameters, and you need a better modeling. Of course, the vehicle dynamics is the most important part here because you need to model the vehicle dynamics very accurately to match this raceline optimization in theory afterwards with your real vehicle behavior. When we're talking about optimization problems, we have always the same setup. We have some optimization variables and we have a defined objective function. That's what I explained to you before. For example, we want to minimize the distance traveled, the shortest path, or we want to minimize the curvature. So here the objective function is lowering the curvature. And that, or what we can do is minimize the lap time. So we're minimizing here the time traveled. Then we have some constraint functions that define finally our optimization problem. When we have created this optimization problem, we need then to run all these mathematical functions, these matrices, in an optimization problem solver. We can choose here from slow ones, we can choose here from fast ones, we can choose here from commercial and non-commercial ones, but finally these solvers are creating a solution for our optimization problem and then hand over this final race line. And that's what we need. And then we get as an output the race line and see the x-y position, the velocity profile and acceleration profile we want to travel afterwards. So now we know how a race line is created and that we need this race line, because if we follow that race line, we will be as fast as possible. But now is the big question: how do we follow this race line? How do we track this trajectory? How do we correct errors? Because you have to imagine, you are now the autonomous car and you see that race line. And now it's for you the time to follow this race line as accurate as possible. And what we are doing here, we are using a so-called controller. I think everybody heard of that from their studies, control theory. And what we are doing, we're trying to track or control the path. And that means for us, we are controlling the steering angle. So what our controller is getting as an input is an error, and distance error, for example, to the race line or to the next point. And the output is the next steering angle. And therefore, we are creating our control loop and we constantly repeat that. So our car will constantly do steering and be or try to follow this race line as fast as possible. In this case here, we show you one particular path tracking algorithm, which is called pure pursuit. So before we start with the pure pursuit explanations, we have to make a few assumptions to understand pure pursuit. So first of all, our vehicle gets the information, the two-dimensional position of so-called waypoints. In our case, this is the race line. Two-dimensional means we are defining the x and y position of a list of points that are on the race line. The second assumption we have here, our vehicle knows where the given waypoints are in the vehicle's frame of reference. That means for us, we have a perfect localization of our vehicle in an x and y frame. We know where the vehicle is, and we know in respect to the vehicle where the next waypoint is. This means our vehicle can localize itself and the vehicle knows the ground truth of its position. And what we are doing now, and that's what you see here in this image, we have the waypoints and we try to follow exactly these waypoints. And these waypoints are followed with one parameter, the so-called look ahead distance. So what we want to achieve is, in the end, we figure out what is the steering angle so we can apply it to the car. Now it's time for us to understand the theory behind it. We start with the following. So the vehicle is in a local 2D frame. The center of this frame is on the rear axle on the car, and we have x and y coordinates. We introduce now the concept of the so-called look ahead distance with the parameter L. What we are doing, we are searching for a waypoint that is in the close to this predefined parameter we calling look ahead distance. That means we now look one distance ahead, for example 1 meter, and we are searching now for a goal point x and y. This X and Y point needs to be on the race line or is referenced on the race line because that is what we want to follow. But here's one thing. Our autonomous vehicle is a robot that is so-called non-holonomic. You can look up the definition, but more or less it means that the car cannot move to any point directly. It has a certain path it needs to follow. This is because of the steering. You know that the car has a steering where both of the tires move, like the front axle steering, and this is called Ackermann steering. This is defined by a maximum steering angle and therefore creates a maximum turning radius. So our car cannot move directly to the left or to the right. It has to follow a certain path, a turning radius. This means for us, our car has to follow an arc. And now it's a question for you. If you look at this picture here, do you see that there might be any problem here for following this arc? Just think about it for a second. So you maybe came up with many problems that can occur, but the biggest problem for us here that this arc is not unique. So we can follow the blue arc, but we can also follow the yellow arc. And you may come to different solutions to come to this point, but we say the main problem here is that this arc is not unique. You may also come up now with ideas like we just try to follow the shortest arc, we try to follow the arc that has the lowest curvature, we want to follow the arc that has the lowest travel time, but this is too complicated and creates a lot of computational overhead. So our solution to make this arc unique, we are constraining the search for the arc, which means the center of the arc, the turning points needs to be on the y-axis. And that's what you can see here, the center of the arc, which means like the turning point, the center of this radius. This one needs to be on the y-axis based on the rear axle of the car. So with this problem we have created now, we have the possibility to solve this kind of geometric problem. Because what we want to get in the end is just the steering angle to reach this X and Y point. So now we have to come up with some simple math. So first of all, the radius of the arc equals the distance y we see here on the y-axis and the distance d. Then we have Pythagoras, d squared plus x distance squared equals r squared. What we do then, we substitute the parameter d and we integrate now our parameter, the look ahead distance. L squared equals y squared plus x squared. You can just repeat that again, but more or less it's normal trigonometry, very easy, just a few bunch of equations which you substitute to each other. But finally, that's what we need. We come up with a relationship between the look ahead distance and the y coordinate of our goal point and the radius of the arc. And that is defined by the radius of the arc is the look ahead distance squared divided by 2 times the y position of the goal point. And this is the equation we needed from a geometric point of view to now help us to come up with the steering angle. Since we know the radius, we can define now the curvature of the arc. The curvature is always the inverse of the radius. Gamma, in our case here, is the curvature of the arc. And now we have the final solution. Our steering angle must be proportional to this curvature so it can follow it. So that's something very easy. You have the curvature, you need just to follow this proportional, which means your steering angle needs to be proportional to this curvature. And that's something you might have seen before because this is a P controller. Now we have our final calculation to do. We have created gamma now, which is the curvature. And we are using here a so-called bicycle model. This bicycle model defines the dynamics of the vehicle. You can look that up. But now we create a relation between the steering angle and between the radius of the arc, which is the look-ahead distance divided by tangent steering angle. And our steering angle delta is then finally 1 divided by r, which means the curvature, which is equal 2 times the y position divided by the look-ahead distance squared. And yeah, folks, that's all we need, which means now we only have to find out the next point. If we know the next point, we get the y coordinate, and the look-ahead distance is something we defined previously. This is our fixed parameter, and now we have the possibility to create the steering angle. That means if we have one point, we create a steering angle, we steering towards this point, then we get the next point and we calculate the next steering angle. And that's all we need, and now we can follow the race line. So the next part in this calculation is the main question. What is the next waypoint? Like, how do we know to find the arc given the waypoints, and how do we pick a current waypoint based on our list of waypoints? Because what we get is our race line is defined by maybe 1,000 waypoints. What is the waypoint we want to follow? Is it the one that is like next to us, or is it the one that is next to us plus 5 meters away? So now how do we pick this goal point? Let's have a look here. What you can see here is again our, for example, a little bit bad race line. That's our waypoints, all the yellow dots. And one of these waypoints is important for us because when we put our car here on the track now, we want to follow exactly that waypoint. But now is the question, how do we find that waypoint? So first of all, we create our look-ahead distance. And what we can do is say we are searching for the waypoint that is closest to our vehicle. That's something we can do. We can also say we choose the waypoint that is closest in look-ahead distance. Like when we make the turning radius and say, hey, here's the look-ahead distance, we have a point that is very, very close to that. And now let's use this one here and try to follow it. But now is the big question. What do we do if there is no waypoint that is exactly the look-ahead distance away from the car? Like, what do we do? Do we search for the closest one afterwards? Or do we search for the closest one that is below in this bubble? So in our case, we have to constrain the search. And what we are doing, we pick the best one that's closest to L. So we calculate more or less the distances from our look-ahead distance to all the other waypoints, and we're choosing the closest one. And that can be in the look-ahead distance or out of the circle of the look-ahead distance. So what should be the value of L in your curvature calculation in your case? That is now the big question. And what we can do here, we interpolate between the points that sandwich the distance L. And with this interpolation, we have the possibility now to create the next search for the next look ahead point, and therefore find the bestest waypoint that we can choose from. Of course, now it's up to you. You can come up with different solutions. You can say, I'm searching differently, I want to minimize, maximize something. But one way to do it, and that's something we recommend, each time we have a new pose of the car, which means each time we update the position of the car, we could find the current waypoint, we actuate, like steer towards the waypoint with a calculated steering angle, and then localize to find the new pose and then repeat. And that's what we do constantly, which means in our update cycle on the car, we search for the next waypoint, we actuate towards the waypoint, and then we localize again. How does this look like in a graphical point of view? First of all, we have our look ahead distance. We are updating the goal point. We are now steering towards this goal point. The car steered, and then we choose the next goal point in our look ahead distance, which is now the red button. And now we do that again. We move forward, we update the position, we search for the next point on look ahead distance and drive exactly towards it. And again, now we have the next point and the next point and the next point. And that creates more or less then the steering of the car. Of course, this algorithm is not perfect. That is the simple solution of tracking a trajectory. The parameter you can vary here, or which defines the behavior finally, is mainly the look ahead distance. For example, if you make a small look ahead distance, for example, like 20 centimeter, this leads to a more aggressive maneuvering to track the tighter arc you created, and the tighter arcs might be against dynamical limits of the car, which means you can easily oversteer the car. Because if you drive too fast and make hard steering to the left, hard steering to the right, you will oversteer the car. Then you have the possibility to choose a large look ahead distance, for example 2 to 3 meters. This leads to a very smooth trajectory, but creates big tracking errors. This means you are probably missing some important information about the steering angle. For example, if you drive to a curve, or if you drive close to a wall, you miss that you need to drive a different curvature and calculate a different angle. So for you, that means you have to tune this parameter very, very carefully, and especially for the racetrack you're driving on. Here you have a wide variety of add-ons you can do, but this parameter is the most important one. Of course, this is just a simple algorithm, and we are not in the end here. You have a lot more algorithms you can choose from. One is the so-called Stanley controller. You see here an image on the right side. Currently what we are doing, we're trying to find the next waypoint. The Stanley controller, for example, is trying to minimize two errors. Number one, you see here the error E, which is the distance error to the raceline. And the other error is the so-called heading error, which means the direction of the car. And both errors need to be minimized, because then I'm following the raceline or these pre-recorded waypoints exactly. This is another algorithm you can choose and tune, and you will see different vehicle behavior. Then number two, linear quadratic regulator, the LQR controller, or the model predictive control, the so-called MPC. Both of them are creating a so-called optimization problem, which means we run an optimization and try to create the best steering angle based on our objective function, again, and based on the constraints. Both of them have the possibility to integrate the vehicle dynamics, which means you can do with both of these algorithms a very accurate steering while taking care of the vehicle dynamic behavior of the car. The disadvantage of these algorithms, they are computationally heavy and need some expertise in setting up the optimization problem and creating the code afterwards, and finally the tuning of the algorithms. Now we are at the end of the theory of the pure pursuit controller, and it's time for you to have a look exactly how this is set up in code.